Okay, so I would like to talk about holography. What is holography? Holography is a duality between, which means it's an identity between two very different looking things. What are the two things? Two sides. You have the quantum field theory side, which we actually call it CFT, the pattern CFT, and ADS. So it doesn't have ADS. On one side of the duality, you have a family of QFTs. Based on Tn, where n is an integer, which tells you roughly how many degrees of freedom are there in the system. For example, maybe you have a theory where the fields are matrices of size n. Okay, so as you change n, the theory changes a lot, a completely different number of fields. On the other side, you have a single quantum system. And n plays the role of h bar, and inverse plays the role of h bar. Well, let's say it's some power of h bar. That some power might depend on the specific duality.
And also view n as a number of a field in quantum field theory.
Yes, I mean, I'd say degrees of freedom, but yes, the number of fields literally scales as some power of n. Well, on the other side, just a h bar scales like power of n, which looks very different to me, right? And the magic to me, one of the biggest magic of holography, that it manages to transfer a number of fields to a Planck constant. Now, a particular consequence of this statement is that large n is semi-classical. And typically, you can organize calculations in the quantum field theory, at least some calculations, in a 1/n expansion. Which will match the perturbative expansion. Now, famously, this side of holography is usually gravitational in nature. And we don't know how to do quantum gravity. So at best, we can hope to do a perturbative expansion. So that in typical holographic situations, you can try to match these two things and call it a duality, but you have no idea how to define that at finite n, so that becomes a definition. You might say, non-perturbative quantum gravity is defined by this family of quantum field theories, and leave it at that. But if you were, very optimistic and you believe that at some point in the future we'll figure out how to quantize gravity, then this becomes a duality. And you might ask, is it really true that if I do quantum gravity with h bar equal to 1/n, I will get precisely the quantum field theory? And I think I've heard often recently doubts about this statement. I mean, it's difficult to believe that the fine-grained details of these quantum field theories as they jump around at the very end will be matched by the quantization procedure. So people might say, no, I think quantum gravity will give me an average of these quantum field theories. And maybe that's true. Now, in the last few years, I've been playing around with something called twisted holography, which are essentially a collection of toy models for holography, simplified example of holography. And in some of those models, we did manage to compute both sides at finite n, and they actually match without any need of averaging or other strain procedures. So now, we don't know how to do quantum gravity, so clearly there are situations where the holographic duality is not gravitational. And you might say, that's bad. I want to learn about quantum gravity, and that's fair. But I believe that these toy models capture at least some aspects of holography that might persist in more complicated situations. I mean, often they are literally a subsector of a fully fledged holographic duality. So my plan for the talk was to just run you through a few very simple examples of holography, which probably no other and the physicists would call holography, but to me, they feel holographic. Okay. So what's the simplest model? So the simplest model is going to be a quantum mechanical system. So 0 plus 1 dimensional quantum mechanics. It's a quantum mechanics of where there are not many large matrices. I don't want too many large matrices because it's hard and because it tends to give you gravitational stuff. So I will still have UN gauge fields. But this at the end just means that you have a UN symmetry and you're passing to UN invariance. And the matter fields are just n times m Dirac fermions, Dirac oscillators, fermionic oscillators. In 0 plus 1 dimension. So literally I have some oscillators, C alpha I, where this runs from 1 to n, and this runs from 1 to m. And I have the conjugates, and some standard commutation relations. Put alpha in one place. So this is a one-dimensional system which has sort of a SUN symmetry acting on it. SUN. And also a UM flavor symmetry acting on it. And I want to gauge SUN, which just means that I want to look at states which are SUN invariants. So I will write some condition like, I don't know, C bar alpha I, C alpha J minus delta ij, C bar C. Let me not write all the indices, yields the states. Okay? So this is my quantum field theory system. And I would like to show you that this system, where n really counts the number of degrees of freedom, can be converted to a quantum system where n is 1 over h bar. Let me see. I don't need to use the side blackboards. Maybe I should use side blackboards. Are these visible to you? Yes. Okay. So let me start from the Fock space of these three fermions. This is, I will write mathematical terminology. I will write it like that. I don't know if this is a useful terminology, but exterior powers of CNM. And so you take this Hilbert space, this Fock space, and you project on SUN invariance. So how do you compute this? There is something called skew Hall duality, which allows you to do the calculation. It tells you what the Hilbert space looks like as a representation of UM. So as a representation of UM, you find the direct sum of irreducible representations for UM, labeled by a Young tableau, which has height n and length and width n. So essentially, these are representations where you have a lot of indices. Roughly, you are anti-symmetrized n at the time and symmetrized capital N at the time. Okay. Do I have to? Let me take the Hamiltonian to be 0 for now. Feel free to. Feel free to. I mean, I'm doing kinematics, no dynamics. But we can later try to add an Hamiltonian and see what happens on the dual side. All the operators that you're going to write are made out of mesons, which are sort of Mij, Ci, alpha, C bar, J beta, which are the UM generators. And plus baryons, which are going to have a lot of indices, and which are built with an epsilon tensor. I'll mostly focus on the mesons, so the baryons are fun too. So let me just give you an example. Let me say take m equal to 2. Then this sum goes from 0 to m. So I have 3 terms. I have just a copy of C. I have Cn plus 1 as a representation, in a irreducible representation of UM, of U2, and then another copy of C. Now, have you encountered at any point recently representations of U2, as U2, say, with increasing spin? Maybe if you read the papers on the fuzzy sphere quantization, for example, you might have encountered them recently. It's just a fact that this Hilbert space as a representation of U2 is the quantization of a nice phase space. So if you take a classical mechanical system with phase space, it just is 2 with the obvious symplectic form, the round volume form. And you take h bar equal to an inverse. The quantization is canonical, and it will give you the reducible representation of a dimension n plus 1 for U2. For SU2. This then generalizes. So this representation is the quantization of the Grassmannian of n-dimensional planes in CM. So in this toy model, you can totally transform n into a quantization parameter. You get a nice phase space, a semi-classical system, which happens to have a nice quantization, canonical quantization, which reproduces exactly the finite answer. So this is my example number 1. Now, it's not, so this is my holographic dual. Classical mechanics, so mechanic, 1D quantum mechanics with phase space, the union of all the Grassmannians inside CM. Now, it's not presented to you in the conventional radius CFT look. You might have perhaps expected to see some two-dimensional system of some sort with a holographic boundary where you find your mesons and baryons. You can do that. It's not too hard. You can use some 2D BF theory or something like that to reproduce this phase space. You can study, you can study the effect of these baryons and their correlation functions, and you can formulate the thing in the language of string theory because it's a gauge theory at the end, SUN gauge theory. So you have a very boring string theory. You have something called D-branes that fill space-time and which implement the fermions. And then you have other D-branes which are sort of zero-dimensional and might or not reach the boundary, which sort of give you excitations to the system, which whose degrees of freedom are really these Grassmannian. Okay, so this is sort of toy model number 1. It's very simple, but I think it captures this aspect of holography. Mm-hmm. Yes, so this. So right, so on this side I have a, there is this baryon number, which is number of fermions, the fermion number divided by n. these different summands at different baryon number. Each of the summand becomes a classical phase space. So you have a classical system which sort of can be in different configurations, each of which is a phase space, like different vacua. It's a direct sum of physical systems. And if you try to do a string theory description, you can say, these zero branes carry baryon number, and dynamically I can have any number of them. And after I decide how many I have, I get phase space and I quantize it. Okay. So this is example number one. I don't know if there's some questions specific to this example. Mm-hmm.
The context of symmetric workflow, people have found it meaning to do a Fourier transform, and is that a natural thing?
Not particularly. I mean, it's strange to Fourier transform in 1 over h bar.
But that can help the workflow string.
Right. The combinatorics of the symmetric orbifolds is quite different from the one of large N theories. So said I don't know if I'm giving any universal statements, but for SUN gauge theories and some, especially for vector models, where you have some very simple collection of matrix fields and some rich collection of vector value fields, then this sort of phenomena happen a lot. So I'm hoping to sort of build up in dimensionality to something more complicated, example by example. Mm-hmm.
The string theory is in what possible?
I'm still trying to figure out exactly how the string theory looks like, because I thought about the example. This example is a simplification of an example where I know the string theory. I'm going to describe next. It's some kind of weird two-dimensional string theory. It's a topological string theory almost for sure, but on some weird target space. But I can give you something more explicit next. Mm-hmm.
The certain Fermat number can always the average Fermat number is N0.
Mm-hmm. Yes.
And then that determines some geometry of the
Yes.
ABS side.
So I didn't put an Hamiltonian here, but I could have. For example, you could have put a 4 Fermi Hamiltonian. That would be a meson bilinear, which according to the rules of holography means that you have changed the boundary conditions of your whatever 2D fields live in the bulk, deforming them in some way. So one could do it. It would be interesting to do so. And with this, modify them. I mean, the Hamiltonian classical is just a function on this Grassmannian, and you can select a point or maybe a subregion, and there will be fluctuations around that. And here there will be some potential. This change in boundary conditions creates some potential on your phase space. Well, really some Hamiltonian again, on the phase space. Not potential, sorry. Now, the next example, it's an Anyon chain. So I'm going to look at the SUN at level kappa. So this is the 2+1 Chern-Simons theory. So this is a 2+1 dimensional topological field theory, or phase of matter, topological phase. It has anyons, which are labeled by representations of SUN, roughly. There is some identification, which I'm not going to worry about. And in particular, I can use any representation. If it's irreducible, I get one Anyon. If it's not irreducible, I'm just going to get the direct sum of the Anyons. And I want to use as representation the Fock space of a 1D fermion. So I want to look at the Anyon, lambda dot Cn. This is essentially the same as coupling 0+1D fermions n of them, coupled to the 3D gauge fields. So if you really have using Chern-Simons theory, you take you make a defect like a Wolfensohn line by putting 0 plus 1 fermions along the defect. If you have a topological phase of matter, you have to find some impurity where you can take this direct sum of antisemitic powers of the fundamental representation. Okay, and I want to take M of these anyons in a nice chain. I'm going to work on the plane, or perhaps you should say S2. I mean, let's just say I want to work on the plane with no charge detectable from infinity. So R2, 0 charge. So this problem is very similar to the previous one in the sense that if I send the level to infinity, the only effect of the SU2 gauge or the Chern-Simons gauge field will be to impose global SUN invariance. And the Hilbert space will be literally the same as the one we looked at before. Now, the Hilbert space is a bit more complicated. You need to take the tensor product of these anyons and pick the identity summand. But you can still compute it. Luckily, some mathematicians did the job for us. So now, just giving you a vector space is not very interesting. It's better to give a representation of something, or some algebra. Here there is an interesting algebra. You can define open string operators, which transfer one index from one anyon to the other. So you sort of make the antisymmetric power jump up here and down here, and you move one box from the left to the right. Let me call this operator EI. And you can also define some Fj that goes in the other direction. And you can define a K, which is just Q to the fermion number. Q is e to the 2 pi I over K plus N. That doesn't really matter. So these are nice operators. They're analog of the mesons I wrote before. Right? If you didn't have the Chern-Simons gauge fields, you would just destroy a fermion here and create it here, or vice versa. They form an algebra, and luckily mathematicians computed this algebra for us. So the algebra generated by the E's and F's and K's is called the quantum group for GLN. So it's an explicit algebra. It has a nice representation theory, which is very similar to the one of GLN. And so the Hilbert space can be decomposed into irreducible representations of this algebra. And the decomposition is identical as before. Except that now, I'm acting with these more complicated generators. By the way, you can ask, why don't I look at more complicated string operators that maybe go around various punctures and far away? Well, it turns out that all the string operators are contained inside here. So that's another nice result. This is really the complete operator algebra, except for the analog of the baryons, which is something where n fermions annihilate, which you can add as some kind of a baryon vertex. But again, I will not discuss it now. And well, now I can ask, is there a nice Lagrangian limit of this structure? So of these representations for this quantum group. Now there is an extra parameter because there is both n and kappa. But holography tells us what to do in these situations. You define a 't Hooft coupling, which is essentially n over kappa. Or better, let me just define a G, which is Q to the n, more convenient. And the idea is to keep G finite as you send n to infinity. And if you do that, you do find a nice classical limit. Which is a weird deformation of the Grassmannian. It turns out that this manifold is quite nice. It has a lot of interesting structure. It's something called a cluster variety. It has a canonical quantization. And this canonical quantization reproduces exactly this representation. So that's nice. Now you could say, why would you use that quantization? Now I can try to elaborate on that. So it turns out that for this system, you can write a nice holographic dual of a more traditional form involving string theory. People have long known that SUN at level kappa has an A-model topological string holographic dual. So SUN K Chern-Simons theory on specific manifolds is dual to a model on some specific geometries. I'm not telling what the model is. It's just, you can think about the theory of fluctuating symplectic forms, but symplectic forms have no local content. You can always put a symplectic form in a canonical form by a change of coordinates. So it's a pretty empty theory. There's almost nothing in terms of fields, but there are interesting D-branes, which are the main actors of the story. Anyway, this is dual to a model on some 6-dimensional manifold. So you can do a picture where you have here, actually let me do it horizontally. You have here your Chern-Simons theory, and there is some kind of bulk. And people also know that these anyons can be described holographically. They describe the presence of an object called a D-brane, which is an extended 3-dimensional object. It's telling you that this object comes to the boundary at that location. If I have many anyons, well, these objects will come to the boundary at many locations, but it doesn't need to be different objects. So one of the fun aspects of D-branes is they can merge. So if you have a collection of anyons, you might have a big blob which reaches the boundary at many locations. And in the context of the A-model, you can ask, what's the phase space of this blob? The phase space is literally the Grassmannian. This is the form Grassmannian. But also, you know what's the volume theory of this blob? So it's a kind of a Chern-Simons theory, and there is another Chern-Simons theory that lives on the blob. So that tells you that if you want to quantize this phase space, well, you just quantize Chern-Simons theory pretty much. It's something you know how to do. And that quantization reproduces precisely this quantization. So this is another situation where you can do calculations of finite n, and you reproduce exactly the finite n answer. Even though, it has, quite some subtle structure. I mean, this is not somehow, it's a more non-trivial statement than it sounds. I don't know how to say this. Even when you quantize the sphere, right? If you take the sphere and maybe you put an Hamiltonian, which is just the height on the sphere, and you do quantization in perturbation theory, you get some modes at the bottom of this Hamiltonian. A perturbative calculation will produce a Hilbert space which just keeps going, called the Verma module. The fact that the Hilbert space truncates, it's a non-perturbative effect. This truncation is quite rich. If you move here, I mean, if you try to tell me how do I truncate a Verma module to give you this particular representation? Well, it's complicated. A bunch of null vectors, you need to know what's happening. Some of the fact that the phase space is compact translates into some complicated structure. And the same is here. So yes, there is fine structure as you vary n, but this fine structure is reproduced by a unitary quantization on this compact phase space. So I think this is a fun lesson. Now I don't know if it will apply to quantum gravity, but it definitely happens in a lot of situations with D-branes. Mm-hmm.
Why do you say that the A-model is not a theory of quantum gravity?
Well, it's a theory of fluctuating symplectic forms. It's a symplectic quantum gravity, yes, but where all the fields are gauge trivial. So quantizing it is not so difficult, except the sum over topologies you might worry about. That's super interesting. So here, what you find on the right-hand side depends on what geometry you put your Chern-Simons theory on. We actually have no idea what's the holographic dual of a generic trimanifold or Chern-Simons theory on a generic trimanifold. If you open the literature, Auguri Vafa will tell you what happens on S3. S3 is fun. For this calculation, I needed R times S2 instead, which is slightly different, but very similar. There is a nice geometry for the A-model, which is R2 times the locus of A squared plus B squared plus C squared is equal to T squared, something like that. Anyway, it's the formula in singularity. And there is a lot of fun in trying to understand D-branes in that geometry. Sorry, there is a... yes. So in this A-model, naively, this is a three-dimensional submanifold, but actually D-branes are a bit more complicated than that. So you need to improve your geometric understanding, do string theory. But you know, the calculation is to be done exactly, and you get that answer. Now, we could try to push this game in more and more dimensions. For example, the next natural step is to look at 3D Chern-Simons, 2+1D Chern-Simons. And maybe put an interface. You can put 1+1 dimensional chiral fermions. The price is that the level jumps by 1 because of the gauge anomaly. So you get a chiral interface between two topological phases. And usually you look at chiral boundaries for topological phases. I prefer to look at this interface because I can do it with sort of this vectorial degrees of freedom without messing up the matrices. And there is a very interesting chiral algebra that lives here. It's a WN minimum model. And you can study correlation functions in this chiral algebra. There is a bunch of currents, which are essentially something like psi dagger, d to the n psi. And you can study correlation functions on S2. And you might want to match this with an holographic calculation. And it turns out you can figure out an holographic dual. Again, the A-model is the same. One of the rules of holography is that if you're just changing the vector matter, you're not changing the string theory. You're only changing the D-branes. So now there is going to be another D-brane, some weird 5-dimensional D-brane called a coisotropic D-brane. Luckily, Kevin Costello studied the volume theory of this D-brane and how to quantize it. So in particular, it's an overnormalizable thing at first sight, but he showed that there is a canonical way to pick counterterms. So it's uniquely normalizable, actually. And so you can do perturbation theory, but there is so much algebraic structure and so much symmetry that you can really do exact calculations again. So you can really do the holographic calculation without knowing anything about the chiral algebra and reproduce exactly the correlation functions at finite n. So this is another example where everything works nicely. Now, my dream at the moment is to do 3D situations. So really do 2+1 dimensional Chern-Simons plus fermions. This would be an interesting theory that, you know, an actual physical theory that you might be interested in, you know. Unfortunately, we do not know the D-branes that you require to put the fermions in, but I believe they exist. So the task is to sort of find the correct D-branes to embed this vector, what is essentially a vector model in string theory and dualography. You can think of different strategies, but you know, my feeling is that if I understand lower dimensional fermions, I must be able to understand 3-dimensional fermions. Worse can to worse, I can make a lattice of them and turn on and take a continuum limit. So I'm optimistic that, you know, sooner or later we can get this right. And this is an example of a big collection of vector models where people sometimes proposed holographic duals in the past in terms of in a language which was completely orthogonal to string theory. But I think now we can put them all inside string theory and sort of connect them with with chains of dualities, which are interesting. And they're not quantum gravity. Well, okay, that's not a fair statement. If I do this with actual physical fermions, there will be a stress tensor in the theory. It will be a meson instead of a single trace operator. So somehow the gravity, I'll have a gravity that lives on the D brane inside the topological string theory. But yeah, it's still gonna be some kind of quantum gravity. Mm-hmm.
There was this holographic duality in the minimal model.
Yes.
Very higher state.
Yes.
How is that related to?
So the Tiger spin theory must be the Kaluza-Klein reduction of this 5-dimensional theory.
When you say phi d, you mean phi space-time?
4 plus 1D. I mean, yeah, if there is one topological direction and two holomorphic directions. Yes, it's a 5-dimensional, non-commutative, holomorphic topological Chern-Simons theory. Mm-hmm.
For the Chern-Simons matter theory, there is like a family of continuous family of Basilian theories. You don't accept that answer?
Sure, but I'm a string theorist at heart, so if I have a string theory dual, I feel happier. And also, I think that sort of putting it in the context of a large N expansion gives you tools which are useful. I mean, it's a bit difficult to work with Vasiliev theory or to understand, why it's there, how to define it. So, in general, the most optimistic perspective on the 't Hooft expansion is that every theory of large matrices has a string theory dual, which might or not be gravitational. It might be very strange or algebraic, non-geometric, I don't know. But if that's true, there must be some algorithm to produce it, right? In a sense, right, standard holography is a collection of exceptional examples. There are very special quantum field theories which happen to have a very special holographic dual. But if I want to make a statement about all theories of large matrices, there must be a systematic way to produce a dual. You cannot sort of have a miracle for every single thing you write down. So, right, I think my general program is to sort of try to understand how to figure out the string theory dual of a large N theory from refining our understanding of the 't Hooft expansion. Okay. Yes, sorry. These are questions, right? Yes.
Phi d theory, how is that related to the 14 Chern-Simons that happened?
So it's different. So this will propose in the context of crystalline theory.
By Kevin. It's essentially a complex symplectic gravity. So you have one topological direction and two which are complex symplectic. And the main field is essentially a fluctuation of the complex symplectic structure. So it's a complex symplectic gravity of some sort.
So it's a bit like up here, like Davide again.